Good afternoon, everyone. My name is Rajan Prasad. I'm here to present my work on the influence of cable routing on cable-driven lower limb rehabilitation exoskeleton. This work has been conducted in collaboration with Khalifa University and Columbia University. So we are targeting this rehabilitation exoskeleton for stroke survival. I will give you a basic idea of a stroke and how it influences people mobility. So if we see the mind of the human body, the left side of cerebral hemisphere control the right side of the body motion while right control the left. In case of accident, injury, trauma, if there is any blockage in either of these regions, this is a state of a stroke where person cannot walk properly. As per WHO, it is the second leading disease causing mortality and third in terms of resulting disability. It results in a hemiparetic gait where person one side body part is impaired, couldn't walk properly, resulting muscle spasticity, degraded muscle strength, abnormal synergic activation. Now, there are different robot-assisted gait training devices are available or being designed in the past and in now. Some of them include treadmill-based devices, foot place-based devices, overground, sitting type, and other exoskeleton orthosis. However, if we analyze in general the current trend, majority of device uses link-based device design where we put motor, actuator, and the heavy bulky links on the user limb which already have a reduced weight bearing capability. Furthermore, such design induce inertia and inertial vibration to the user and assume knee joint as a pin joint, which actually violate the biomechanics of the knee joint itself. Now, to overcome these limitations, we decided to go with a cable-driven exoskeleton, basically, which works as a remote actuation device. We can put our actuator somewhere in a remote location far away from the impaired limb. It doesn't require exact joint alignment as it acts as an end-effector approach. It results in a very lightweight design and exert very minimum inertia and inertial vibration to the user. Now, to model this cable-driven rehabilitation device, we model the lower limb of user as a link-based model where we have two-link pendulum and we derive the dynamic equation of motion using Euler-Lagrange formulations. And we also model this cable in a mathematical form using vector projection principle. Furthermore, the anthropometric of user is being scaled to the model using Winter-based model, which is based on a height and the weight of the user. Furthermore, the reference helix trajectory is taken from Fukushi dataset with a slow walking speed of 3.48 seconds to mimic the stroke slower walking speed. We came up with a three model where we have a first model, we have a long cable alone. Then we put first intermediate hinge to guide the cable. And second, we put two intermediate hinges to guide the cable. So these hinges in blue will only guide the cable, providing a free movement of the cable through itself. We simulated these models and found that the joint angle tracking were similar in all of these cases. So to further differentiate, we analyzed the cable tension and joint force component being induced on them. And we found that with each addition of these hinges, the cable tension increase. So the peak cable tension magnitude keep increasing and it is further reflected in an impulse, which is area under these curves. So by introducing the cable hinges, we increase the overall impulse requirement by the cable tension by 8% almost, while the joint force component that are being induced because of the applied cable tension increase by average of 11% in both of the configurations. Here are the simulation of these three models. So where we can see in first case, the cable goes far away from the limb, while in second and third, it remains close to the user limb. So that means we provided a restrictive movement of the cable, reduced the possibility of cable vibration by segmenting it in a small segments, and we mitigated the chance of being entangled with the user limb or other body part. In conclusion, we provided a framework to assess the different routings and its influence. And by introducing the intermediate hinges, we are likely to increase the joint force being induced on the user and the cable tension required to move the exoskeleton. However, such design provided a restricted movement of cable and reduced the chance of cable entanglement and vibration. Further investigation with different configuration are required to give a more insight into this design. Thank you.